Welcome back to Things I Know Nothing About, where we dive deep into topics we barely understand, hoping to emerge slightly wiser today. Maya, we're talking about something truly mind blowing that could redefine our place in the universe.
Oh, Alex, I am so ready for this. When you first mentioned this study, I immediately thought of all those science fiction stories and movies, but the fact that this is real science happening now is just incredibly exhilarating. We're talking about a 2026 study that narrowed down the search for alien life to a mere 45 planets, which is such a specific and tantalizing number.
It really is. The sheer scale of this achievement, going from over 6,000 known exoplanets, a number that itself is staggering when you think about it, down to a highly curated list of just 45 rocky worlds, is a testament to how far our astronomical capabilities have come in recent years. It feels like we're genuinely on the cusp of something monumental here.
It definitely does. This groundbreaking research was published in the monthly notices of the Royal Astronomical Society in March 2026, led by astronomers at Cornell University with Abigail Bull et al. At the helm. They embarked on this truly ambitious task, sifting through an enormous amount of data to pinpoint these specific targets, and it's truly a monumental effort that captures the imagination.
And it's not just a random selection. Their methodology was incredibly rigorous, leveraging data from some of the most advanced instruments we have available. They used information from the European Space Agency's Gaia mission, which provides incredibly precise measurements of stellar positions and distances, alongside the NASA Exoplanet Archive, which is a comprehensive database of exoplanet properties. This combination allowed them to perform such a detailed analysis.
That precision is absolutely key. Because when you're looking for planets light years away that might harbor life, every single detail matters. The primary criterion for their selection, and one we hear a lot about in the search for extraterrestrial life, was the planet's location within what scientists call the habitable zone, or HZ. This is that sweet spot around a star where temperatures could potentially allow for liquid water to exist on a planet's surface.
And liquid water, as we understand it, is considered a fundamental requirement for life as we know it, right? It's the universal solvent, crucial for biochemical reactions, and really the bedrock of all terrestrial life. So, finding planets in this Goldilocks zone is the first crucial filter in this incredibly complex cosmic sieve.
Exactly. They initially identified 45 rocky worlds within this broader empirical habitable zone, which is a great starting point. But what's even more fascinating is that they didn't stop there. The researchers then applied a more stringent set of criteria informed by advanced 3D climate models, which further refined this list to just 24 planets within a narrower 3D HZ. This is where it gets really interesting for me.
That distinction between the empirical and 3D habitable zones sounds incredibly important. What exactly do these 3D climate models account for that makes them so much more stringent? And why is that level of detail necessary when we're talking about conditions for life? It seems like a significant leap in our understanding.
It's a huge leap, Alex. The narrower 3DHZ approach considers factors like atmospheric effects, such as how a planet's atmosphere traps or reflects heat, and planetary rotation, which influences how heat is distributed across the surface. These elements profoundly affect surface temperatures and, critically, the stability and long-term presence of liquid water. A planet might technically be in the empirical HZ, but if its atmosphere is too thin or its rotation causes extreme temperature swings, liquid water might not be stable, making life much harder to sustain.
So it's not just about the distance from the star, but also how the planet itself interacts with that stellar energy, factoring in things like its atmosphere and how it spins. This makes perfect sense. Earth's atmosphere and rotation are absolutely critical to our stable climate, allowing liquid water to persist across most of its surface. It's a much more holistic view of habitability.
Absolutely. While liquid water is paramount, as we've discussed, the science of habitability truly encompasses a complex interplay of many different factors, not just temperature. The study's criteria likely went beyond just the habitable zone, also looking for planets that are rocky and relatively small, ideally no larger than about twice Earth's radius, because larger planets tend to be gas giants, which are less likely to support surface life as we understand it.
That's a critical point. We're looking for Earth analogs, not just any planet with liquid water. So, beyond size and rockiness, what other specific criteria were they considering? I imagine an atmosphere plays a huge role, not just in temperature regulation, but also in protection from harsh cosmic conditions.
You're spot on, Alex. The presence and composition of a protective atmosphere are absolutely crucial. It's not just about regulating temperature. An atmosphere shields a planet from harmful radiation like UV and X rays from its host star, and could potentially harbor key biosignatures, those chemical indicators of life we hope to detect. Without a robust atmosphere, even a planet in the perfect temperature zone might be barren.
That makes sense. And speaking of the host star, its activity must be a huge factor too. I've heard about red dwarf stars, for example, being prone to intense flares. How does a star's behavior, including things like flares and radiation, impact a planet's atmosphere and its ability to retain water over geological timescales?
Stellar activity is indeed a massive consideration, especially for planets orbiting red dwarfs, which are the most common type of star in our galaxy. These stars, while long-lived, can be incredibly active, emitting powerful flares and intense X-ray and UV radiation. This radiation can literally strip away a planet's atmosphere over time, especially if the planet is orbiting closely, which many habitable zone planets around red dwarfs do. So a planet might start with water but lose its protective atmospheric shield.
That's a serious challenge for habitability, even if the temperature is right. It's a delicate balance. Another factor I've heard mentioned is tidal locking. Can you explain what that means and how it might affect a planet's potential for life, especially when one side is perpetually baked and the other perpetually frozen?
Tidal locking is a fascinating and common phenomenon, particularly for exoplanets orbiting close to smaller stars, like red dwarfs. It means that one side of the planet perpetually faces its star, much like our moon always shows the same face to Earth, while the other side remains in eternal darkness. This creates extreme temperature differences, with one side scorching hot and the other frigidly cold.
So, how could life possibly thrive under such extreme conditions? It sounds incredibly challenging. Is there any scenario where a tidally locked planet could still be considered habitable, or are we mostly looking for planets that rotate more like Earth with a day-night cycle?
Well, this is where the complex interplay of factors truly comes in. While the temperature extremes are a major hurdle, a very thick atmosphere or a large global ocean could potentially help regulate and redistribute heat across the planet, creating more temperate zones. Scientists even hypothesize about a terminator zone, the twilight strip between the light and dark sides, where temperatures might be just right for liquid water to exist, potentially supporting life. So it's not an automatic disqualifier.
That's a truly intriguing thought, a twilight world where life clings to the perpetual sunset or sunrise. It really expands our understanding of where life could potentially arise. What about orbital characteristics? Are planets with highly elliptical orbits also considered, even if they swing in and out of the traditional habitable zone, experiencing extreme seasonal shifts?
Yes, absolutely. The study even considered planets with highly elliptical orbits to test if worlds could remain habitable despite those extreme seasonal shifts. This pushes the boundaries of our traditional definition of the habitable zone. It's like asking if life could survive on a planet that experiences a super summer followed by a super winter, or if geological activity could replenish the atmosphere even if it's periodically stressed.
That's really pushing the definition of habitable. It suggests a much broader, more resilient picture of life than we might initially assume based solely on Earth. So, beyond these dynamic environmental factors, what about the planet's intrinsic characteristics, like whether it has a magnetic field or ongoing geological activity?
Those are absolutely critical for long-term habitability, Alex. A planetary magnetic field is vitally important because it acts as a shield, protecting the atmosphere from stellar winds and coronal mass ejections. Those powerful bursts of plasma and magnetic field from a star. Without a strong magnetic field, a planet's atmosphere can be slowly eroded away, leaving its surface exposed and potentially sterile.
So, a magnetic field is like the planet's personal force field, preserving its ability to hold onto water and a breathable atmosphere. And what about geological activity, like volcanism? How does that contribute to a planet's habitability over billions of years?
Geological activity, such as volcanism and plate tectonics, is incredibly important for several reasons. Firstly, it contributes to a planet's volatile inventory, meaning its initial water content and other crucial elements. Secondly, ongoing geological processes help regulate a planet's climate over long timescales through cycles like the carbon silicate cycle, which can draw carbon dioxide out of the atmosphere or release it, helping to stabilize temperatures. This is vital for long-term habitability, providing a stable environment for life to evolve.
So, it's not just about having water initially, but having mechanisms to keep it and its atmosphere stable for eons. This really paints a picture of a planet as a dynamic living system itself, constantly interacting with its star and internal processes. Now, let's talk about some of the specific planets that actually made the cut in this study. Are we talking about the usual suspects, or are there some new, exciting names on this list of 45?
We've got a mix, Alex. Some familiar names and some lesser-known gems that are incredibly exciting. Among the most promising candidates identified by the study, the TRAPPIST-1 system is definitely a standout. It's located about 40 light-years from Earth and is famous for its 7 Earth-sized rocky planets.
The TRAPPIST-1 system always captures headlines, and for good reason. 7 Earth-sized planets around a single star is just wild. Which of those planets specifically made it onto this refined list, and what makes them particularly interesting in terms of habitability?
The study specifically highlighted TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1g as being within the habitable zone, receiving stellar energy levels comparable to Earth's. While TRAPPIST-1b, c, and d are generally considered too close to the star and TRAPPIST-1h too far. More optimistic scenarios suggest any of the planets could potentially harbor liquid water. This is especially true given their likely tidal locking, which, as we discussed, could create temperate zones at the terminator line between the perpetually lit and dark sides.
That's a fascinating thought that the very characteristic of tidal locking, which presents challenges, could also create these unique temperate refuges. It means we have to really broaden our definitions of what a habitable environment truly looks like. So, the TRAPPIST-1 system remains a prime candidate with multiple shots on goal, so to speak.
Absolutely. It's like having several lottery tickets in one system. Next up, we have Proxima Centauri b, which always gets a lot of attention because it's the closest known exoplanet to us, at just 4.2 light-years away. It absolutely remains a prime target for observation and research.
Proxima Centauri b, the nearest neighbor. That proximity makes it incredibly appealing for observation, but I recall there being significant challenges to its habitability despite being in its star's habitable zone. What are the main hurdles for Proxima Centauri b that make its potential for life a more complex question?
Indeed, its habitability is quite challenged. While it orbits within the habitable zone of its red dwarf star and has a minimum mass of 1.3 Earth masses, it faces a tough environment. Its likely tidal locking means those extreme temperature differences, but more critically, it's subjected to intense UV and X-ray radiation from its active host star, Proxima Centauri. This powerful radiation could easily strip away its atmosphere, making it very difficult for liquid water or life to persist on its surface over geological timescales.
So, even the closest known exoplanet, a tempting target, presents a real conundrum for habitability. It really underscores how complex this search is and how many layers of criteria we need to apply. Are there any other familiar names on this list that have been in the news for a while?
Yes, Kepler-186f is another well-known candidate that made the cut. It was one of the first Earth-sized planets found in the habitable zone of another star, discovered back in 2014, and it continues to be a planet of interest for astronomers. It's exciting to see it affirmed on this new, refined list.
Kepler 186f is indeed a classic example often cited when discussing potentially habitable worlds. It's good to know that earlier discoveries are holding up under this more stringent analysis. But what about some of these lesser known gems you mentioned earlier? Are there any that are particularly intriguing or surprising additions to the list?
One that stands out is LHS 1140b, often dubbed a super Earth. It's approximately 48 light-years away and has shown tantalizing hints of being an ocean world. Observations from the James Webb Space Telescope, or JWST, have even suggested a significant amount of water and a retained atmosphere, which is incredibly promising for habitability. This is exactly the kind of planet we want to investigate further.
An ocean world 48 light years away with a retained atmosphere. That sounds like a truly exciting prospect, especially with direct JWST observations supporting it. That's getting us much closer to actual characterization, not just theoretical modeling. What other interesting cases made it onto this expanded list, especially those that challenge our traditional notions of habitability?
The study also included planets like TOI 700 Eeg, K2-3D, and TOI 715b. What makes some of these particularly interesting is that they have elongated orbits, which, as we touched on earlier, challenges the traditional definition of the habitable zone. These planets move in and out of what we might consider the ideal temperature range, suggesting that habitability could persist despite periodic extreme seasonal shifts. It's a testament to the resilience of life, or at least the conditions that support it.
That's truly fascinating, thinking about a planet that might undergo dramatic climate changes throughout its year but still maintain conditions for life. It suggests that our definition of habitability needs to be far more flexible and inclusive than we might have initially thought. This kind of research is really pushing the boundaries of astrobiology.
It really is, Alex, and this focused catalog of 45 planets is not just a list, it's a roadmap. It's expected to guide astronomers in prioritizing future observations, especially with advanced instruments like the James Webb Space Telescope. JWST is already playing a crucial role in characterizing exoplanet atmospheres, and its capabilities are truly revolutionizing the field.
The JWST is an absolute game changer. What specific kinds of observations is it making, and what key biomarkers are astronomers looking for with it? I imagine detecting actual signs of life, or at least the building blocks for it, is the ultimate goal.
With JWST, astronomers are meticulously searching for key biosignatures in these exoplanet atmospheres. These include gases like methane, oxygen, water vapor, and carbon dioxide. Detecting these in certain combinations, or at unexpectedly high concentrations, could provide compelling evidence of biological processes at work. The telescope's infrared capabilities allow it to peer through atmospheres and analyze their chemical composition with unprecedented detail.
That ability to analyze atmospheric composition is incredible. Has JWST already yielded any exciting results or challenged previous assumptions about exoplanet habitability, even before focusing on these 45 new candidates?
It absolutely has. JWST has already provided tantalizing hints of oceans on exoplanets like LHS 1140b, which we just discussed. It has also detected atmospheres around rocky worlds like 2OI 561b, which actually challenged previous assumptions about their ability to retain atmospheres, especially around smaller stars. These early findings are incredibly encouraging and suggest that we might find more atmospheric diversity than previously thought.
That's fantastic news, showing that some of these planets might be more resilient than we gave them credit for. It builds a lot of excitement for what JWST will find when it turns its gaze to these 45 prime candidates. But what comes after JWST? Are there even more powerful telescopes or missions on the horizon specifically designed to push this search further?
Yes, the scientific community is already planning for the next generation of observatories. Future missions like the Habitable Worlds Observatory, or HWO, the Habitable Exoplanet Observatory HABEX, and the Large Ultraviolet Optical Infrared Surveyor LUVOIR are being designed with the explicit goal of directly imaging Earth-like planets. This is the ultimate dream, to see these worlds directly, not just infer their properties.
Directly imaging an Earth-like planet around another star, that would be an absolutely monumental achievement, changing everything. What kind of capabilities would these future observatories need to achieve that? And what else would they be looking for once they can directly see these worlds?
These next-generation observatories would need incredibly advanced optics and instrumentation, including large mirrors and potentially starshades, which are separate spacecraft designed to block out the blinding light of a host star, allowing the faint light from its orbiting planets to be detected. Once they can directly image these planets, they would then study their atmospheres in even greater detail than JWST, searching for even more definitive signs of life, beyond just basic biosignatures, to truly answer that profound question: are we alone?
That vision of future telescopes directly imaging exoplanets and studying their atmospheres directly for incontrovertible signs of life is truly awe-inspiring. It feels like we are living through a golden age of astronomy, with each new discovery bringing us closer to understanding our place in the cosmos. This study, narrowing down the search, is a pivotal moment in that journey.
It truly is, Alex. When you think about it, this study significantly refines the search for life by narrowing down over 6,000 known exoplanets to just 45 strong candidates. That's less than 1% of the total discovered exoplanets, which is a truly remarkable level of focusing our efforts. It's like finding a few needles in a haystack that's now been reduced to a very manageable pile.
A very manageable pile indeed. And then, the identification of 24 planets within that stricter 3D habitable zone further highlights the rigorous selection process. This isn't just a hopeful guess, it's a scientifically informed, highly curated list, providing an invaluable catalog of opportunity for targeted research. It gives us a clear path forward.
Exactly. It means that every minute of observation time on JWST or future telescopes can be used with maximum efficiency, focusing on the world's most likely to yield exciting results. And while the search results indicate significant funding from NASA and ESA for exoplanet research and the development of future observatories, such as the NASA postdoctoral program and the Habitable Worlds Observatory concept, the specific funding details for this particular probing the limits of habitability study itself weren't explicitly stated beyond the general agency data used, which is fairly common.
That's fair. The funding for specific studies can often be rolled into broader agency budgets, but the fact that major space agencies are investing so heavily in exoplanet research and these next generation observatories speaks volumes about the scientific importance and the public interest in this quest. It's truly a global endeavor.
It absolutely is, this study. And the incredible work that went into it fundamentally shifts our perspective. We're moving beyond just finding planets to actively identifying worlds where conditions could be right for life. It's no longer just a hypothetical concept, it's a tangible, observable goal with real targets.
And it's not just about finding life, which itself is a complex term. It's about finding the conditions for life, which is a huge step. Even if we don't find little green people right away, understanding the diversity of potentially habitable environments tells us so much about the universe and how life might arise in different contexts.
Precisely. It broadens our understanding of what life could be, how it could evolve, and the various environmental niches it could occupy. Our definition of life is so Earth-centric, so these discoveries help us to think more broadly, more universally. This study helps us refine our search parameters and pushes us to imagine possibilities beyond our own limited experience.
It's almost like a cosmic census, trying to figure out how common or rare our own situation is. Is Earth a fluke, or is it one of many similar worlds out there, potentially teeming with diverse forms of life? The implications are truly profound, affecting not just science but philosophy and our very sense of self.
That's it, Alex. The question, are we alone, isn't just about finding another organism, it's about understanding the fundamental nature of existence. This study provides us with a concrete, actionable list of places to look, giving us the best chance yet to answer that question within our lifetimes. It's an incredibly exciting time to be alive and to witness these scientific breakthroughs.
It truly is to think that within a few decades, we might have definitive answers, or at least much stronger evidence about life beyond Earth is exhilarating. This list of 45 planets isn't just a list, it's a beacon of hope and a testament to human curiosity and ingenuity.
And it reminds us that the universe is far more vast and full of possibilities than we can even begin to imagine. Every time we narrow down the search, we expand our understanding of what's truly out there and what other forms of existence might be waiting for us to discover. It makes me feel incredibly small, but also incredibly connected to this grand cosmic tapestry.
Absolutely, this has been an incredible journey through the science of exoplanet habitability and the cutting edge research that's bringing us closer to answering one of humanity's oldest questions. Thank you, Maya, for breaking down such a complex and thrilling topic for us today.
My pleasure, Alex. It's truly a topic that sparks the imagination, and I'm always thrilled to talk about the ongoing search for life beyond Earth, especially when we have such concrete, exciting results like this study. The future of astrobiology is looking incredibly bright.